Hey guys, Mr. Rast here, and we're going to do a little biology throwback for you right now. The male part of a flower is the stamen, and the female part of a flower is the pistil. What did the stamen say to the pistil? You know what he said? I like your style. I like your style. That's what he said. It's a good pickup line. That's how I met my wife. That wouldn't even make sense. What am I talking about? All right, guys, let's just do this. Let's just do this, okay? So, topic 13. The fourth lesson here, we're going to put some calculations involved with our equilibrium that we've been working on. So we've been doing some equilibrium, and now we're going to put some numbers in with what we've been learning. So to do this, we're going to have to rely on some skills that we should know at this point. And these skills are, first, naming, writing ionic formulas. This is something that we did back in topic 6, I believe. You got to be able to write and name ionic formulas so we'll talk about that in a little bit. You need to be able to balance equations. Writing chemical equilibrium expressions. This is what we've been doing in the prior lessons with this topic is writing equilibrium expressions. And you're going to have to be able to remember and apply your mathematical orders of operation. So when do you divide, when do you use the powers and the roots of things? And finally, you got to be comfortable using your scientific calculator. There's going to be some issues here, or some calculations, some work that you're going to have to do. And every scientific calculator is a little bit different, so you got to practice yours. You got to learn to use yours. It's a tool that you need to be proficient in. So, all right. So in review, we're talking about we have to be able to write ionic formulas. So writing ionic formulas, just a little review. If you think you know this, why don't you pause it and just try it right now. Can you write the chemical formula for aluminum fluoride? If you're a little rusty, let's go through this right here. So we first list the symbols, and this is based off of the periodic table. The location on the periodic table, aluminum is +3 and fluoride is -1 based off of their locations on the periodic table. So let's take a look at this real quick. Remember, everybody, in this row is +1, +2. Transition metals can vary. This row would be +3. That's aluminum. That's +3. Plus or -4, -3, -2, -1, and this group here does not have a charge. So just a reminder on ionic formulas. So aluminum would be +3 and fluoride would be -1. So this is based off of location on the periodic table. The next thing we're going to have to do is write out the symbols. Always put the cation first. Remember, the cation is the positively charged one, and then we're going to figure out what would be the least common multiple between these two. So we have a 3 and a 1. The least, because remember, we're trying to balance out these charges here. We're trying to balance these charges out. So the least common multiple between a 3 and a 1 is a 3. And so aluminum goes into 3 because aluminum has a charge of 3 just once, and fluoride goes into 3 because it's -3 times. We've done this a few different ways in class. You might remember it like this. You'd have aluminum, which is +3, and fluoride, and we might talk about crossing the charges down like something like this. So that would mean, now we get rid of the charges, we're crossing the numbers. So there's a 1 here. So there's just a 1. We don't write ones. And then the fluoride would be a 3. Another thing that we did in class is we did stuff like we kind of just took a look. If aluminum is a +3 charge, remember we made these little square papers like this. Aluminum has a 3 charge, and fluoride is just a 1 charge. So we'd have to have 3 fluorides to negate, to cancel out all those positive charges of the aluminum. So that's why there's 1 aluminum and 3 fluorines. So there's different ways that we've looked at this stuff. Whatever, just refresh your memory on the way that you remember how to write this stuff. But it's very important that you're capable of writing these ionic formulas. You also want to review your polyatomic ions, I'm going to be very nice to you guys, and I'm going to only use polyatomic ions from this list here. There are more that we did talk about with this lesson, but you should be able to write any formula with polyatomic ions and be able to use the periodic table. If you want more practice writing ionic compounds, which I highly suggest you should be honest with yourself and do before this test, go back to lesson 6, this should say topic. What the heck? Okay, and with the magic of editing, it now says topic 6, lesson 1. So go back there and get more practice with your polyatomics and your writing ions if you need a little refresher on that stuff. The next thing you got to be comfortable with is balancing equations to do this stuff. So remember to balance equations. So let's write the balanced equation for the dissociation of calcium bromide into aqueous calcium and bromide ions. So to do this, we first have to be able to write the formula for calcium bromide, and that's what I mean about the ionic compounds. So determine the charges of both the calcium and the bromide. Based on their positions in the periodic table, we see that calcium is a +2, and that's because it's alkaline earth metal. It's in the second column, and bromide's in the 17th column. It's one away from the noble gases. It's Br negative. I know that font makes that negative look like it's a really strange R, but that's Br negative. So the ionic formula for this would be for every calcium, you would need 2 bromines. So it's a +2. We'd need 2 bromines because they're only -1 to cancel out that +2. Remember, ionic formulas do not have a charge. Finally, let's write the balanced equation for the dissociation. So we're going to talk about calcium bromide breaking into aqueous calcium and bromide ions. So the calcium bromide is a solid, and if it's going to dissociate in solution, we're going to make calcium ions, and we would have 2. See, there's two bromide ions. This also, if you refer back to lesson 3 in equilibrium, this is also a KSP formula. So it's a solid dissolving into ions. You have to be comfortable with all this stuff. So practice again balancing equations if you need to. Practice again naming ionic formulas if you need to, ionic compounds. Okay. Writing K values. Let's do a little bit of practice on this. So let's write the K for this calcium bromide. So we determined the calcium bromide dissociation would look like this. And remember, when we write the Ks, we take the products over the reactants. So the product is calcium and bromide. We raise the power of these concentrations to the coefficient. So since I got 2 bromides, it's bromide squared. And it would be over the denominator would be the reactants, but we don't use solids or liquids because they don't have concentrations in our equilibrium expression. So we only use aqueous and gases. That's all we're going to be using in my class for this, okay? Okay, so let's take a look at another one. Let's do the concentration constant for this formula here. We've got an iron 3 chloride plus 3 moles of water yields iron 3 hydroxide and 3 hydrochloric acids, 3 moles of hydrochloric acid. So again, we're going to put the products over reactants, and then we're going to have, one of the iron 3 hydroxides, and we're going to say the hydrochloric acid, but we're going to have that to the cube root because of this coefficient, and it's going to be over the iron 3 chloride, which is here. We're not going to include the water because it is a liquid, so that would not be in the expression. So the Kc for this reaction would look like this. So just reminders on how to set this stuff up. These are all things you need to be able to do to put the numbers in there. So here's our first example with some numbers. When the reaction below reaches equilibrium at 400 degrees Celsius, don't let this temperature throw you off, because when you change the temperature, you change the K value. So if we're going to talk about a K, it's appropriate to talk about at what temperature this K was recorded at. You're not going to do any calculations with equilibrium that are going to have anything to do with the temperature. You're not going to use that in your calculations. It's just proper to list at what temperature you recorded this, because you could say, well, I got a different K for that. Well, what was your temperature? It just changes, okay? Things dissolve better, they dissolve more at higher temperatures, so the K value would change, the concentrations. Anyways, we've got this reaction here. We got nitrogen plus 3 hydrogens yields 2 ammonias, and the concentrations are 0.15 molarity for the nitrogen. Hydrogen is 0.80 molarity. Ammonia is 0.20 molarity. Let's figure out the K value here. So the first thing we should do whenever we're doing these problems is take a look at what is in the question. Let's list it out so we're not looking at the words, but we can just kind of look at the information. And so I'm putting the molarities of the different concentrations we have out there, and I'm also writing out here what the constant of the equilibrium concentration constant is, because that's what we're calculating. So I know what I'm solving for and I know what I have. The second thing you do is kind of analyze this. How can I get this information to here? What kind of equation do I need? What kind of conversion factor do I need? That's the second step, is what do I need to do this? Well, since this is equilibrium, we're going to be using equilibrium expression, the equilibrium constant. And that's what we've been practicing here, and we just did that in the last slide. How could we write the equilibrium expression for this reversible reaction? It would be products over reactants. So to write the equilibrium constant, we're going to put the products over the reactants, and don't forget that since there's a coefficient 2 here, that product concentration is squared, and the reactants, we have nitrogen and we have hydrogen, which is cubed. So we have this here, and if you take a look at, if you pull out information and then you figure out what you need to solve it, you can see that you can just start plugging in things. The nitrogen is here, the hydrogen would be here, and the ammonia would be here. So you just plug in these numbers and solve. So let's do that. If we plug in these numbers for here and we solve, practice right now. I really would like you to have a scientific calculator in front of yourself and practice. Put these numbers in your calculator and make sure that you're getting the same numbers I am, because some people just need a little fresher up and they're not comfortable with their calculator. It's important to learn to be comfortable with your calculator before a test or quiz. So when you put these in there, you should get 0.52. I'm not putting units in these K values because a lot of times K values are listed. There's a whole bunch of K values, and every equation would have different units here. For instance, this one here would be 2 molarities on the top, because this is molarities that we're looking at, right? So they have 2 molarities on top, and you'd have 3 on the bottom. I'm sorry, 3 plus 1, so 4 on the bottom. So this would actually, the unit would be 0.52 per molarity squared. Sometimes they cancel out completely. It's going to be different all the time. We're just going to leave them out. It's not really the focus here, and also when we table it, we don't want to have these strange units all over the place. Okay, so don't worry if you don't see the units, that's okay. This one's a little more challenging. In this situation here, I'm giving you the K value, but I want to know what is the concentrations at equilibrium. So we're going to have pure water, and we put solid silver chloride in this pure water. And in the water, it's got a K value, and it's a very small K, meaning it doesn't have a lot of product. If it's a small number, that means it doesn't have a lot of product, which happens to be the ions for KSP. So this is a rather insoluble situation here. How much would be left over? So let's take a look here. We have our K value, and we know that this is a KSP. That means it's a solid dissociating. That's what KSP means for silver 1 chloride. Remember, silver 1 chloride doesn't mean that there's one silver necessarily. It means that the charge of silver is +1 when you do transition metals. And chloride, based on its position on the periodic table, we know is -1. So if it's a 1-to-1 ratio, it's just silver chloride. And it dissociates into silver ions and chloride ions. We want to know what is the concentration of the silver and the chloride ions. The equilibrium expression for this would be the silver chloride, and there's no coefficients, so there's no powers here, and there's no denominator because this is a solid. So this would be our equilibrium expression right here, and I can put in the KSP as so. So this is where we're going to start working at here. We got some good start here, but we got to analyze this a little bit further before maybe we can completely answer the question. Let's take a look here. So with this equilibrium expression, for every unit of silver chloride, for every 1 mole of silver chloride that dissociates, it's going to produce 1 mole of silver and 1 mole of chloride. It's a 1-to-1 ratio, see, because there's no coefficients here. So if it's a 1-to-1 ratio, and we take a look at our equilibrium expression, when this dissociates, you're going to have equal amounts of silver and you're going to have equal amounts of chloride because it's a 1-to-1 ratio. If they're the same number, we can just substitute the same value for them. So x times x is going to be 1.6 times 10 to the -7th. So that's x squared equals 1.6 times 10 to the -10th. Sorry, I think I might have said 7th. X squared equals 1.6 times 10 to the -10th. So to figure out what this x equals, it would be the square root. And I really want you to check this out on the calculator you're going to use for tests and quizzes. Make sure that you can take the square root of this. And it sounds simple, but you take a calculator you're not comfortable with and you can't figure out how to do it. And I'm not teaching you how to use your calculator during a test or quiz. So please practice this right now. Make sure that you can take the square root of 1.6 times 10 to the negative 10th and get this number here, 1.3 times 10 to the negative 5th molarity. So this is the concentration at equilibrium of X. And remember, X is both the silver and X is both the chloride. So X is the silver and the chloride, and it's 1.3 times 10 to the negative 5th. Okay, in this problem, you're going to be using barium nitrate here, and we have a different KSP, 4.64 times 10 to the negative 3rd. Everything else is the same as the last problem, but this is barium nitrate that's going to cause some problems. So pause the video now, see if you can just write down on your piece of paper what you think barium nitrate is. And hopefully you gave that a try. Unpause. Barium nitrate is, remember, barium has a +2 charge and nitrate is a polyatomic anion, NO3 negative. So the proper write-up for barium nitrate would be BaNO3, NO3, and there'd be 2 of them. Because nitrate, right here, this is nitrate, has a negative charge and barium has a +2 charge, so it would take 2 nitrates to balance off with the 1 barium. So this part here is important that you're capable of doing that just from the words here. If you need to, review prior lessons in this topic, review topic 6 where we talk about ionic formulas and stuff like that, but get yourself comfortable that you're able to write this if you know it's a KSP of barium nitrate. Remember, KSP is the dissociation of a solid. We need to figure out the concentration of the barium and the concentration of the nitrate at equilibrium. So if we set this up, what is our expression look like? Well, it's the products over the reactants. And our products is barium times nitrate squared, the concentration of nitrate squared, and it equals our KSP. Okay, so for this setup here, we're going to take the barium. We have to take note here that for every unit of barium nitrate, it's going to produce 1 barium ion, but it's going to produce 2 nitrate ions. So when this dissociates in water, you will not have equal parts of barium and nitrate. We'll get 1 barium but 2 nitrates. So this equilibrium expression would be the concentration of barium times the concentration of nitrate, and that concentration is going to be squared. But these are not X and X. Remember, this is going to be twice as concentrated as the barium. So the nitrate's twice as concentrated, so we would say that barium, if we say that's X, then the relationship nitrate would have to it would be 2X. It's twice as concentrated. And on top of which, it's going to be squared, because that's the equilibrium expression. So we're taking a look at concentration separately from the expression here. So the concentration is going to be doubled, and the formula is also going to have a factor in here too. So now we can do some math. So we got to practice our order of operations and rearranging some stuff in here. So when we square something that it's on the outside of the parentheses, that means both the 2 and the x has to get squared. This whole thing has to get squared. In other words, it's 2x times 2x. And 2x times 2x would be 4x squared. So it's squared. It's 2x times 2x. So we have 4x squared. So that would be the same as 4x cubed, because 4x squared times x. And now to solve this, what we would do is divide by 4 and then take the cube root of that. So we want to practice this. Divide this number by 4 and then take the cube root of your answer, and you should get 0.105 molarity. That's what your x is. And we've already determined that x is the barium. It is not, this is not the concentration of the nitrate. Nitrate is 2x, so we'd have to multiply this number by 2, and that is our nitrate. Our nitrate is 2x. That's the concentration of the nitrate. Okay? So this would be the answer to number 3. I got 2 practice problems for you to do right now. I would really like you guys to pause the video and give these a try. And then unpause, and we'll go over it. So pause right now, do your best, try these 2 out. And hopefully you just did that. And so let's work them out. Let's take a look at these 2. So the first one, you should have, by the way, these 3.2 molar, 0.21 molar, and 0.78 molar respectively means it goes in the same order. So that's your hydrogen iodide, this is your hydrogen, and this is your iodide concentrations. Oops. So in this question here, that's the second one. In this question here, this is our balanced equation, and we're solving for the K. So we know from the question, though, let's write what the expression is. So Kc equals, the expression would be the hydrogen concentration times the iodide concentration divided by the hydrogen iodide concentration squared. That would be how we would represent this. It's a hydrogen here. That would be how we'd represent this. And now let's actually plug in the actual values that we have here. So I'm going to put the values right above what they are. So it said that the hydrogen, this was 3.20 molar, because it was respectively, so 2 molar and 0.78 molar. So that would be, the hydrogen would be 0.21 times 0.78 divided by 3.20 squared. So let's plug that in your calculator and see what you get. And this is what I'm going to get. I'm going to do it right now. So 0.21 times 0.78, and I'm just going to do it the long way, divided by 3.2, and I'm going to divide it again by 3.2 because it's squared. And so what I've got here is 0.01. I've got two significant figures, so 1/6 would be my Kc. And that's it. You could have written it in a scientific notation also, which would be 1.6 times 10 to the 12, -2. That's the same answer. You could have written it either way, and that's great. Let's take a look at our second question here. Our second question is, if we have a KSP for aluminum hydroxide, what is our concentrations? So to do this, we're going to have to first take a look at what aluminum hydroxide is. Aluminum has a +3 charge and hydroxide has a -1 charge. So therefore, aluminum hydroxide would be AlOH3. I would have to have 3 hydroxides to balance out the +3 charge here. I'd have to have 3 negatives to balance that out. And this is a solid, and it's in equilibrium. We're dissociating because I have a KSP. It's dissociating into aluminum, and that's aqueous, plus 3 hydroxides, which is also aqueous. So next thing I would want to write is, what is our KSP? What's our formula for this? KSP equals the aluminum concentration times the hydroxide concentration cubed. Okay, we know the KSP value, but before we plug in that KSP value, I'm going to say, I'm going to switch this out. Well, I guess I could put in the KSP value. Let's just do that. 3.00 times 10 to the -34th equals the aluminum, if that's X, for every 1 aluminum that you form, when this dissociates you get 1 aluminum, but you get 3 hydroxides. So that's X times the hydroxide, which would, since it would take 3 of them, that would be 3X, and that's going to be cubed. The hydroxide is 3X. So if we're going to rearrange this around, 3.00 times 10 to the -34th will equal X times, we factor that out, 3 cubed. That's 3 times 3 is 9, times 3 is 27. So that would be 27x cubed. Because remember, this is 3x cubed. That means it's 3x times 3x times 3x. So that's why it's 27x cubed. Now we can put that x over here. 3.00 times 10 to the negative 34th equals 27x to the 4th. So to solve from this point here, I am going to divide by 27, and then I'm going to take the 4th root of that. So let's take this. 3 times 10 to the 3 times 10 to the negative 34th. Okay, yep, 3 times 10 to the negative 4. That was supposed to be negative. Did that not work? 3 times 10 to the 34 negative. There we go. That's better. So that's 3 times 10 to the negative 34th. And then I'm going to divide by 27. Divided by 27 is this. And then I'm going to take the 4th root of that. So I'm going to raise that to the 4th root on this calculator here. I'm going to raise it to the 1/4 power. Raise to the 1 divided by 4. That's the same as the 4th root. So I'm raising that answer to the 1/4. And I've got this number here. So x equals 1.83 times 10 to the negative 9th. That's what my calculator is saying here. And that's x. And x is also aluminum. So that is aluminum's concentration. But hydroxide is 3x. So 3x equals, well, let's take this answer and multiply it by 3. Times 3 is 5.48 times 10 to the negative 9th. And that's 3x, and 3x is hydroxide. That's our hydroxide concentration. We could put those brackets here because that's concentration, or the molarity of these two. Okay? I know it's a lot to digest. Practice it. Take a break. Practice it again. Make sure you can use your calculators properly. Make sure you can review your ionic formulas properly. And I look forward to seeing you soon. Good luck.